The remit of the Barnett Award keynote, it's quite broad, and I thought I would focus on one particular problem, which is an important problem in environmental science and across the sciences more generally, and it exemplifies the kinds of things that I think work in a collaboration between statisticians and non-statistical scientists with interesting problems to solve. So that's how I've come up with my topic and my title, which is how to tune your simulator. So there are lots of applications in science where we construct a computer simulator for a process which is transformative. That is to say, something happens, if you like, at the upstream end of a natural process. Right? Things happen in the process, and then something emerges at the downstream end, the system output, if you like. We see these across the sciences, but we see them a lot in environmental science. So the one that I've got here as an example is from flood modeling. This is the Y catchment, and I live in Hereford, which is a bit fuzzy, that, isn't it? Just there. That's Hereford. Now, Hereford is prone to flooding. What that means is that if there's a heavy rainfall event in the Y catchment, then people in Hereford experience flooding about 8 to 12 hours later. And the Environment Agency is aware of this, of course, and they would like to do things to ameliorate the flooding in Hereford from a heavy rainfall event. So they would build a simulator of the Y catchment, and that simulator would be forced by a rainfall event. So the rainfall event goes into the simulator at the upstream end, right? And then the simulator does stuff, and at the bottom it produces a time series of river depths in Hereford, from which they can then assess the degree of flooding. And the purpose of building a simulator of that process is because then you can look at different potential interventions into the catchment on a cost-benefit basis to see what is a good way, if there is such a way, to limit the flood damage in Hereford from a heavy rainfall event on the Y catchment. So the kinds of things you might look at is, could we build an early warning system with demountable defenses in Hereford, which is actually what we have at the moment? Could we put larger defensive structures in place upstream? Would it be beneficial, for example, to dredge the river downstream of Hereford to move the water on faster? Would it be possible, for example, to take grazing land in the upland part of the catchment and reforest it? Right? Those are the kind of questions that you would answer with a computer simulator, because you would put each of those interventions into your simulator, you'd send the same large rainfall event through your simulator, and then you'd look at the impact upon the output of your simulator, which is river depth in Hereford. So that's the kind of thing that I'm going to talk about today. The challenge is, when we build a simulator of a complex process like the Y catchment, we know that we're not going to capture all of its subtleties. Nature is far too subtle for us. We do the best that we can, but we appreciate up front that our simulator is going to be very imperfect. And moreover, it's going to contain within it tuning parameters that are not perfectly understood by us. And it could be that those tuning parameters are describing parts of the system that we haven't bothered or can't observe, like the subsurface structure of the soils, for example. Or it could be that they're standing in for processes that we don't completely understand, like the effect of water removal by evapotranspiration. Now, we don't want to ignore those completely, so we put in some kind of holding function, if you like, that attempts to capture to first order processes that we don't understand, and we have tunable parameters in those holding functions that we hope to adjust to bring our simulator into alignment with what the system is actually doing. So what you end up with is, and this is just a toy example, is you have a measured forcing event. So you have measured rainfall on the Y catchment. You've got in situ monitors, and you've got rain radar and so on. So you have a pretty good idea about the spatial temporal process of dumping water onto the catchment in one particular event. And then you actually have measurements downstream in Hereford, say, where someone has stood in the river in wellies with a stick. It doesn't actually happen like that, but that's how I imagine it happens. And they have recorded these measurements This is a different experiment entirely, but you get the idea. So you have a pulse that's traveling through Hereford as a result of the forcing pulse that occurs upstream on the catchment. And that's what you see, right? That's what you see from the system itself. That's real system data. And then you build your simulator and with all its imperfections and so on, and with all its standing in processes and with some tuning parameters that you set to their central or best values as you first imagine it, and then you put the rainfall event into your simulator and you run the simulator, and what you get typically is not a very good match. You would struggle, I think, to persuade your client or your funder, right, that this was a good simulator as it stands for understanding the effect of large rainfall events in the catchment on the river depth in Hereford. So the question is, you run your simulator once and you've got a bit of a horrifying outcome, right? You're going to need to adjust the tuning parameters to bring your simulator output more in line with the things that you've measured. So the question is, how do you get from here, right, which you cannot sell to your client, to here, right, which you can sell to your client? And how do you do that as efficiently as possible? I mean, if you had thousands and thousands and thousands of runs to burn, I think this would be a moot point. You would just go ahead and just churn through, right, a high-resolution grid in the parameter space and find the best fit. You would just do that. But these simulators can be very expensive to run. We're talking minutes, I guess, for a reasonable catchment simulator. In other areas where I work, in physics, for example, sometimes you can do a batch of 20 runs over the course of a weekend. That wouldn't be uncommon. In climate science, it actually takes months to do a single run, from the past to the present and into the future. So we have to find ways to do this efficiently. That is, to move from here to here, right, efficiently in a small number of simulator runs, because only then will we be able to tackle the really big problems that describe the effects of transformations through really complex processes like the climate. So a brief outline of what I'm going to propose. There is already an approach to doing this problem, and it's ubiquitous in the sciences, which is simply to create a misfit function between the simulator output and the measurements. And that misfit function is almost invariably the sum of the squared deviations. So it's very common in practice, so I go back to the picture, to simply take the squared difference between the black line and the center of the red bar. You can scale it by the observation error if you want to, square all those and sum them and then create a misfit function. And that is basically what's done at the moment, right? You do your fitting by minimizing the root mean squared error. Yeah, that is, we'd call that the engineering approach, but it's much wider than just engineering. It happens almost everywhere. Now, what I want to talk about is how we as statisticians can add value to that approach, right? So I'm not talking about a radical reinvention of the procedure that currently happens. I'm talking about taking the current procedure and adding value to it, right? Making it a bit better, but not in such a way that you move entirely beyond the realm of what people were previously doing. So I tend to stress, when working collaboratively with other scientists, the need to find incremental improvements on current practice. That's value added from the statistician, if you like. And that's what we're going to explore today, whether as statisticians we can add value to the engineering approach by trying to be a bit more realistic about the problem that we're trying to solve. So the two things that I'm going to cover are, first of all, I'm going to propose a formal model which links the parameters of the simulator output, the system output, and the measurements all together in one package. And that model is going to be quite explicit about the fact that the simulator has its limitations. So it's going to represent explicitly the idea that the simulator cannot capture all the richness of the underlying system. And in that kind of model, for reasons that we do understand, you tend to get smoother log likelihood functions. And then we can exploit the smoothness of the log likelihood function in a richer model of the relationship between the simulator and the system to do a much more effective optimization. So we're going to do statistical optimization as the second part of this approach. So those are the two things that I'm going to cover. And there's nothing revolutionary about what I'm suggesting. The objective really is to illustrate how you can take an existing procedure and you can make it better. Stats value added. So I'm just going to rush through a bit of notation because, of course, that's traditional. Basically, X would be a sequence of time points in the simplest possible case because we're tuning to a time series. Bold F is a time series of outputs. Theta is the value of the tuning parameters that you plugged into your simulator and run it to get bold F of theta. And likewise, we have matching system values, the y's. That's a vector of system values, which we don't observe. So we get to see this every time we run the simulator, but we don't understand the function f because it's very complicated. But when we run this f at theta, we get to see f of theta. We don't know the true system values, but we do know their observations. Okay, so it's 3 vectors there. Now, this is really the key thing where I think as statisticians we can add value, right? We think about how it's possible to relate an imperfect simulator to the system that it purports to represent. And there's really 3 components to this relationship. And this is based upon work that goes back for 15 or 20 years, really, where we, particularly with Michael Goldstein and colleagues in Durham, we've tried really hard to understand how one can relate runs of an imperfect simulator to one's beliefs about the underlying system. And there are 3 components. The first component is that there is, in a sense, a best value of the parameters, right? Over all the possible choices that you can make for the tuning parameters, there is, in a sense, a point in that space which is the best value. And that best value can be described formally by sufficiency properties, but we're not going to go there today. We're just going to acknowledge that there is a best value, which I'm calling theta star, right? So somewhere in the parameter space, there is the thing that you're looking for, right? The best setting of the parameters, which is theta star. And then what we recognize is that even were you to find theta star and to run the simulator at theta star, you would not expect to get a perfect match between the simulator output and the system. And you'd expect there to be imperfections of 2 types. The first type is that it's quite possible that there would be an offset. So here is you running the simulator at theta star, right? Here is the system value, but forget the distributions and so on. Here is an offset, right? The whole of the simulator output might be displaced vertically, either upwards or downwards. Now, that often happens in practice. In fact, it happens so often in climate science that it's given a name, bias correction. In climate science, it's very common to run your simulator through the past and into the future. And when you run it through the past, you compare it to historical observations, and you find that there's a bias in, say, the temperature field of maybe 1.5 degrees. Globally. So what you do is you continue to add that bias to the future output of your simulator as well, and that's known as bias correction. So we're not making up the idea that there might be an offset. It's very well recognized in lots of situations that there might be a vertical offset between what your simulator is producing at its best input value, theta star, and what the system is doing. So we allow there to be a vertical offset, which is very simple in this case. I mean, you could make it into a process, a temporal process, but I've just made it into a constant. And the other thing is that we recognize that even allowing for the offset, it's quite possible that your simulator with the offset will still not match, right, the system values. That is, the offset is not enough to correct your simulator at its best parameter value theta star. So we recognize the presence of a stochastic process called the discrepancy that sits between alpha plus f of theta star and the system values y. That discrepancy is captured here by a variance matrix, because remember that bold F and bold Y are both vectors. So this is a variance matrix of discrepancy terms. And we'll have more to say about that in a second. So that really that's the off-the-shelf model, if you like, for capturing the limitations of your simulator. You say, okay, there is a best input, theta star. We don't know what it is, but it's a thing that we're searching for. And on top of that, even when we find it, right, we may need to make a vertical correction to the simulator output. And even after we've made the vertical correction, right, we may still not be able to match perfectly between the corrected simulator and the system value y. Right? So this is a temporal variance matrix. And that captures systematic errors in your simulator that aren't part of the vertical offset. Now, if you start with this model and you integrate out the thing that you don't know, which is y, you can create a likelihood function, right, using the observed values of the output, of the system output, z-obs, if you like. And that likelihood function is going to have 3 sets of parameters in it. There's the the theta star, that is the best setting of the parameters which you don't know. There's the alpha, which is the vertical offset, which you don't know. And there's the discrepancy variance, big K, which you don't know. Okay, so one can construct a log likelihood from this model, but it has three sets of parameters in. And the thing that we're really interested in, of course, is the theta star. That's the thing that we want to find. But clearly, alpha and big K are sitting in the way. Okay, so our problem here really is, hey, we want to talk about theta star, but we have these two nuisance parameters, big alpha and big K. And the question is, what do we do about those nuisance parameters in order to focus our attention on theta star? Well, the engineers have a solution, right? The solution is set them to 0, right? That is what happens in the engineering solution. We set all the description of the simulator's limitations to 0. We behave as though the simulator is in fact perfect. We say, hey, there is no vertical offset. Hey, there is no discrepancy, right? We'll set them to 0, and then you get back to root mean squared error. That is, you simply sum the squared deviations between the simulator output and the observation, and you scale by the measurement error, and that gives you your misfit function. So that's clearly what the engineers are doing in this case. They are genuinely treating a simulator, which we all recognize is imperfect, as though it were perfect according to this model, right? So this is an opportunity for us statisticians to do better, right? Can we do better than pretending that our imperfect simulator is actually perfect? And the answer is, yes, I think we can. So I'm going to do this in 2 stages. The first thing is we want to reduce, if possible, that matrix K, which is n by n, where n is the number of observations that we have, to a scalar. That would be much more convenient. So what I'm going to do drastically is I'm going to imagine that the discrepancy is stationary, and then I'm going to thin the observations to the correlation length of the discrepancy. So I'm going to remove, if you like, 9 out of every 10 observations, and keep every 10th observation in the belief that the correlation length between observation 1 and observation 11 is basically is shorter than that distance, and so we can treat those as uncorrelated. So this is a drastic step. I'll talk more about this at the very end. But thinning the observations, right, is a very cheap way, basically, to sidestep the issue of a complex variance matrix. So I'm going to assume stationarity and then thin. And if you do that, you end up with quite a straightforward log likelihood, because there's no worries about off-diagonal elements in the variance matrix K, because they've all disappeared due to thinning. So that's the first thing. And then what we can do next is, now we have 2 scalar parameters, we can profile them out. Okay. That is, we can, if we're minimizing the negative log likelihood, then we can basically, for every value of theta star, we can minimize over alpha and little kappa, to create a log likelihood function, which is a function of theta star alone. Okay. So that's my proposal. I'm not claiming at all that this is awesome statistics, right? I think if we were starting from scratch with a problem like this and it was really important, we might even go in a different direction entirely. We might fire up our MCMC or our PMCMC and do all sorts of cool stuff. But what we have here is an incremental improvement on current practice. So it's very much the case that if you're working with a group of scientists who are trying to minimize the root mean squared error between their simulator output and the system observations, right, it's easy to point out to them that they are behaving implicitly as though the simulator were perfect when they recognize that it's not. And then it's easy to go on to say, hey, I've got a framework where we can recognize the simulator's imperfections, but at the same time we end up with a likelihood function which, like your likelihood function, is still only a function of the parameters theta star. So that's what we're aiming for here. We're not aiming for awesome stats. What we're aiming for is incremental improvements on current practice. And this thinned and profiled likelihood, right, is an incremental improvement on setting both alpha and big K to 0. So that's the bottom line. Now, that's all of the theory out of the window. Let's talk about a simulator. Now, of course, I could have built a simulator of the Y catchment, but that would have been a lot of work. And who's got the time these days? So I built my own simulator out of buckets. And the bucket simulator is I recommend it to you, actually. It's a fun simulator. So imagine that you've got a stack of buckets, and each bucket has a hole in the bottom, and it sits above the bucket below, and each bucket has a lip of a certain height. So you get slow flow through the buckets. You force the top bucket with an input with a flux of water. You get slow flow through the holes in the bottom of the bucket into the next bucket and so on. And then if you put too much water into the top bucket, you get fast flow because you overspill the lip. Okay, so if you really put a huge wodge of water into the top bucket, you can get like a spillover from all the buckets. Okay, so you can conduct these buckets in series, which is what I've done here, or you could be a bit more creative and you could connect them through a network. That would be fun too. But this is the bucket simulator, and for each bucket you have two parameters. You have the diameter of the orifice, which is the hole, and you have the height of the lip. And the thing that you measure, so there's the diameter of the orifice of bucket 2, there's the height of the lip. Those are parameters, tuning parameters if you like, and these are the things that you measure. You measure the height in each bucket. Okay? So much more fun to build a bucket simulator than to have to build a huge simulator of the Y catchment. So this is what happens with a 5-bucket system. So I'm going to imagine that nature is running a 5-bucket system. Okay, so it's quite complex. And I put this forcing into the top bucket here. This is a flux. Right? And then I measure, with a state-dependent observation uncertainty, the depth of water in the bottom, but that's the 5th bucket, which is this sequence here. Okay, so this goes into my top bucket. This comes out of my bottom bucket. And we're treating this as nature. So nature is running the complex 5-bucket system. When I build my simulator, I won't give myself nature's complexity. I'll build a simulator of 3 buckets. So, I'm guaranteed that my simulator cannot capture the richness of nature because I've used fewer buckets. That's why I did it this way. I wanted to put clear space between what nature was doing and what my simulator could do. So we're going to ask the question, can I capture the behavior of this 5-bucket system by carefully tuning a 3-bucket system? That seems to me a good analog for the kinds of things we do in practice with imperfect simulators. Now, how about thinning? So the machine learners are onto something here, right? I say thinning because that's what we're doing, isn't it? We take a sequence of points and we drop 4 out of every 5. We thin down to 1 in 5, okay? Thinning is what we do. I think statisticians are quite pragmatic. But if you talk to an engineer about this, they become horrified because you're throwing away 4/5 of the data, and they really don't like that at all, okay? So you have to find a different way to present it. And the machine learners call this feature extraction. It's the same thing, but it sounds so much better. It's like hidden inside the data, there are features which you extract. It's like thinning, feature extraction. Yeah? So I've got a tip for everyone here. When you have to thin something, don't call it thinning anymore. Call it feature extraction. It's the same thing, but it sells much better. So we need to extract some features, right, from this time series. I'm going to thin it, obviously, but so I've just got a few pragmatic choices to make here about how we would thin this data set. I'm going to drop the really noisy ones. Remember, each observation is recorded with a measurement uncertainty, so let's just drop the really noisy ones. They're not super helpful for us. I think that the underlying system is trying to do something fairly smooth, so I'll run the smoother through the remaining points. Then I'm going to throw away some of the points that look really odd compared to the smoother. That's technically a bad move because it's a different model to the one I'm fitting, but it seems to help in practice. And then I'm going to thin the remainder by choosing a subset of points, which I think capture, using my judgment, what I think is really important about this curve. And the thing that's important about this curve is basically the fact that it goes up and comes down again. We want to know, where does it go up? How high does it go? What happens when it comes down? Okay, so I've chosen some points here which capture that basic idea that this bit here is really important, right? So I've got points in there, but of course we want our simulator basically to be right at the start and also right at the end. So I've ended up with 13, unlucky, wasn't it? 13 points out of the original 100 or so, right? So I don't say to the engineer, oh, I threw away 87 points and kept 13. I say, I extracted 13 features from your data, right? And that seems to go down much better, right? So that's what I did. I extracted 13 features from the data. Now, as I said before, I'm running a 3-bucket simulator to make sure there's no possible way that I can actually match nature. There's a built-in imperfection. I'm missing 2 buckets, basically. So this is what happens when we actually run the simulator. So this is the very first run. I'm going to click through these rapidly, but you can see, so here are the data with my thin points as well. This is the first run of the 3-bucket simulator at the central values of the parameters, right? This is the same parameters, but remember there's an extra tuning parameter that I have, which is the offset alpha, which can be a bit tuned. So that said, hey, this line is far too high, pull it down. So we do get a slightly better fit in this case from the thinned and profiled first run. Now, as I click forward in steps of 5, like a poor man's animation, isn't it? Then what you will see is that 2 things to note. First of all, as I'll clarify later, the thinned and profiled likelihood, which remember is just a function of the parameters, it moves more. That is, it improves itself more often as we use the downhill simplex optimizer. So it makes more choices that are better than all the choices so far in terms of the misfit function. And the second thing that you'll see very clearly is that according to our understanding of this picture, it does fit better as well. So if I just go forward a little bit, so you can see it running through here, 25, 30, 35, 40. Now, you can see at 40, let me just go back and show you, 35, they were both neck and neck at this point, weren't they, right? My thinned and profiled likelihood and the engineering likelihood using the downhill simplex optimizer. They've both done 35 runs, and they're pretty neck and neck. This point here, something goes wrong here for the original, and the thing that goes wrong, as you'll probably understand, is that Ri is drawn to the peak. I mean, that's clearly what's interesting for us. And the reason they think that the original has gone wrong here is because it's missed the peak. But it doesn't know that the peak is important, right? I sort of encoded that by my feature extraction. But what it sees is, hey, I can get a much better fit down here, right? And up here, where there are tons of points with very small standard errors, standard deviations. So this move, right, in the engineering likelihood from there to there, right, it looks terrible to us, but it looks good to the root mean squared misfit function because it's capturing better these 2 tails, which we think are less important, but it doesn't know that. Okay? So if we carry on, 45 runs, the question is, can the original get back? Right? Can it get back on level pegging? We're going to run it out for 70 runs here and see. So you can keep watching now. Well, it's not doing very well. There we are at 70. It never really got back. Yeah, it got locked into a good fit in the 2 tails, which we don't care that much about. At this point, I think we'd have to say that the thinned and profiled likelihood is producing a better output in terms of its match to the observations than the original engineering likelihood. So, what happens next? I set myself a budget of 100 runs in total to see how well I could do to simulate this sequence with my 3-bucket simulator. And so I've got 30 more runs to play with here. And what I decided to do then was to use the fact that, in fact, the misfit function for the thinned and profiled likelihood is quite smooth. You can sort of see that in this picture here. That's a picture from the old slide. I'm going to skip over that. Right? But if we had had the new slides, we could have seen that the thinned and profiled likelihood moves more often. It more often makes a good choice about where to go next. Now, I want to move on, though, to talk about how we can exploit the smoothness of the thinned and profiled likelihood function in a statistical optimizer. Some of you will be familiar with the idea of Bayesian optimization, which is what I'm talking about here. Here's a brief slide on Bayesian optimization. We're going to fit the negative log likelihood, that is the misfit function, with a Gaussian process. And that Gaussian process is going to be parameterized by a mean function and a variance function, and they are going to be smooth functions of theta. Now, the idea is that when we're looking to run our next point, right, what we'd like to do is we'd like to find a point with a big expected improvement. Now, the improvement function here is, hey, if you choose a theta, right, and your new point, right, is not better than your best point so far, then just truncate that at the best point so far. But if your new point is better than the best point so far, then return the value of the new point. So this is a criterion which sort of hunts around, and it's small in regions of the parameter space theta, right, where there's a realistic chance of getting a good new run. Now, the reason for using this function here is because it has a closed form expression for its expectation, And you can see right away here, which I think is fascinating, that this expectation captures the two different things that we worry about when we're doing optimization of an uncertain function. We always think about the two things are exploit and explore. Right? The function is uncertain, and so sometimes you want to go off into a corner of the space where the variance is very high and do a run there because it will be highly informative, right, about the function in quite a wide range of theta values. That's the explore step. But exploit says, hey, no, you're running an optimizer. Just go to where you think the function is smallest and keep running around there. Yeah, because obviously in the end we want to find the point where the log likelihood, the negative log likelihood is smallest. So if you look at these two terms here, this is like an explore function. It says, remember we're looking for low values here. It says, hey, go where the variance is big. Right? Because doing a run at a theta where the variance is big will tell you a lot about the function. And this is the exploit step. It says, hey, no, go where the mean is small, right? Because that's you're trying to minimize the function, so a small mean is obviously a good start. So the point about this criterion here is it provides a very natural expression of the trade-off between the exploit part of statistical optimization and the explore part of statistical optimization, which is why I like it. Now, the other thing to recognize about this expression down here is that if you've built a Gaussian process for your negative log likelihood, right, then evaluating this thing here is very, very quick, right? It's basically a fully vectorized operation. It happens in the blink of an eye. You can put 500,000 points, right? 500,000 different choices of theta through here and get the answer in a second, yep, which is quite a lot of points and enough to fill a 6-dimensional space, which is the size of our parameter space. So the nice thing about this is that you can do a grid or any kind of space-filling design across your parameter space really, really quickly. Now, you may not want to stick with the grid, but it's a really good place to start, right? Dump a grid of points down, and you almost immediately get, right, the objective function for every single grid point. Now, that allows you to construct a really quite simple adaptive optimizer. So what I've done here is I've started with the points I've done so far. That's 70 runs in this is a 2-dimensional projection, by the way, of the 6-dimensional parameter space. So you're not seeing 4 dimensions, but you'll get the idea. So these are the points where I've done the run so far in black. Here's a 2-dimensional projection of my grid in blue open circles. This is the best value of that criterion, this criterion, on the grid. That's the best grid point in blue. And then what I do is to get off the grid, just for a bit more fun, I run a quasi-Newton optimizer starting at that grid point to climb up the local hill, or actually technically to go down the local valley. Okay? So one extra run, you do all these grid points, right? You find the best one, and then you initialize a quasi-Newton method, and then you end up here. Okay? So let's watch this going forward, because I find it very relaxing to watch dynamic things like this in action. So there we go. We did this run. So that's saying, hey, do this run here in red. So we do it, so that becomes black, and then we get a new proposal for blue, and we move off it slightly to get red. Right? Oh, okay. So this is definitely an explore run. Okay, it's saying, hey, in this corner we have a ton of uncertainty about what the function is, so let's go there and resolve that uncertainty. We're not expecting that to be a great value, but it's going to do a good job of reducing the uncertainty of the function in this area here. So we do that run. Yeah, it was a bit rubbish, but we keep going. So I'm just going to roll forward here. We're clearly moving in the direction of the y value, aren't we? This is a parameter here which is going somewhere, right? It's on a journey, as we say, right? It's on a journey, as are we all, of course. But this parameter is on a very specific journey. Okay, and it's going, and it's going, and it's going. Still going, still going. It's on a really serious journey, this parameter. Of course, we can't see 4 dimensions of parameters that are also moving. They're also on a journey too, but this one is on its own journey. And I think at this point here, we run up against the top end of the parameter range, so I don't think it can go any further. So it keeps mooching around right at the very top there. So that's what happens in Bayesian optimization. You can do an adaptive search, and you can take advantage of the fact that the criterion that you're optimizing can be evaluated in fully vectorized form in just a second or so for 500,000 points. So that's what I did here. So here's some details. Guenberger's robust GASP emulator, which I really like. It's got a linear and quadratic trend because this is a log likelihood, so we are expecting the appearance of quadratic features, centered, of course. I dump a 500,000 point grid into the parameter space, and then to get my first stage optimization, and then I run forward with a quasi-Newton method with lower and upper boundaries to reflect the parameter space, the parameter box itself. So when you do that, this is what you see as a result. So at run 71, we were here. This is our best run so far, right? The first thing that happens is that this is the new grid point in blue. This is the quasi-Newton improvement in red. We actually run at that value, and in fact, the thinned and profiled log likelihood actually returns a value that's up here. So that wasn't great, but we're learning. And then here's another one. Okay, we're looking for an improvement here. We run again. That one doesn't do very well either, but we're learning. And then here, this one turned out to be pretty much bang in the middle of where we thought it would be. That's good. These are the two random ones that right in the corners. You can't even see the dots there. We run the simulator because it thinks it's a good choice on an explore basis, but in fact, the dots are way up there. Okay, up there somewhere. But then after that, it sort of locks in, and this is that parameter going on a journey. So you can see that we are not improving our best value for theta at every step, but we're doing a lot of improvement as we go along. And in fact, at the point where I stopped running the simulator because I was pretending I had a budget of only 100 runs, we were still improving. And I think if you saw that, you would go to your client and you'd say, give me more money, right? We can keep going here, right? Because there will come a point where this does actually bottom out. Yep. But this wasn't it. So I would be showing this to my client and saying, hey, I need more time on your computer because we can do even better. But we stopped at 100. Now, let's do another comparison just for fun again. So imagine that we keep running the engineering log likelihood using the downhill simplex method, which is a good method. Remember, there's no chance of our function being differentiable, so we would need something that was capable of handling quite rough objective functions. So here it was stuck basically at this bad choice where it was paying more attention to the tails and less attention to the hump. So if we just watch it going forward, this is just another relaxing slideshow. You can see that the thinned and profile, it keeps moving, yeah? Whereas the original is really stuck, right? It's struggling to get out of a local minimum, basically. Oh, now it started moving. We've only got 10 runs to go, so it's got a lot of catching up to do. No, didn't make it. Okay, but we understand why. If we do the maths, then it's quite easy to see that engineering likelihood, it's really lumpy, right? The surface is really lumpy. It's hard for any numerical optimizer to move around a lumpy surface. The point about the thinned and profiled is, for reasons that we do understand, it's just a much less lumpy surface. So when you're going looking for the global minimum, it's easier to move around that surface, so you get there faster. And that's what you're seeing here. After 100 runs, we have to say the thinned and profiled log likelihood has done a good job, but the original is sort of stuck. And in fact, I did actually check, and even according to the sum of squared deviations criterion, the thinned and profiled does a lot better. You can see it improving down here. Now, part of that improvement is the availability of an extra parameter. That's the offset alpha. But you can see that it's really moved away in terms of fit. Even according to the engineering fit, it's doing much better. So I think we're offering here the opportunity to improve on the engineering solution using the engineer's own criterion by thinking about this problem in a more statistical way. So I have some extensions which I'm not really going to talk about. Obviously, this doesn't have to be a time series. It could easily be a spatial problem. For example, you could be dealing with GPS stations over North America, and then you have the interesting question about whether to thin them or whether to aggregate them. And I think that's an interesting question that we might talk about in the Q&A. But you can do that. I'm doing one experiment at the moment where we have two time series, and basically we have two parameters that are particular to each time series, right? So, and then we have two parameters that are common to both. So the two parameters that are particular are about the experimental setup, and the two parameters that are common to both are buried in the physics. Okay, so that's a 6-parameter problem, which is really quite complicated, but the same basic principles apply. And then also we can do prediction, and we can do a little bit better than just plugging in. So to summary, we do recognize the limitations of the simulator. by building a statistical model which has both an offset and a discrepancy. Thinning the observations allows us to reduce back to a profiled likelihood, which is simply a function of the parameters, like the engineering likelihood is just a function of the parameters. Like I say, profile likelihood is a bit mysterious, but it does seem to deliver in this case. Downhill simplex optimization works fairly well at the early stages, definitely for a Bayesian approach in the later stages, because the downhill simplex optimizer has the feature of basically straddling the minimum. It tends to overshoot and then contract inwards. And that's good. If you're trying to fit a Gaussian process to the log likelihood, you don't want all your points in the training data set to be to the left of the minimum. You sort of want it to be straddled. So it works well from that point of view. We switched to Bayesian optimization in the second stage. That's much less easy to do with the engineering likelihood, which is much more lumpy. Okay? This idea about Bayesian optimization is designed to exploit underlying smoothness in the function that you're trying to minimize. And while there are no guarantees, we hope this approach produces a better estimate of the best input for the same number of simulator runs, even under the original criterion that was used, the mean squared error. Great. And that's all I wanted to say. Thank you.
Thank you, Jonty. That was wonderful. Thank you very much indeed. We have some time for questions now, both from the audience here in Manchester and also online. Those online, if you want to put in the chat on the online system, and those of you in the audience, if you can raise your hand. A gentleman here, if you can go to the microphone just at the top of the stairs there, please. If you could announce who you are and any affiliation, that would be great, thank you. And the same for people online, if possible.
Yeah, hi, it's Paul Terrell. I'm an independent consultant. And I loved that talk. That was great, so thank you very much, very refreshing. I could ask you several questions, because there's lots of different topics, but I'm about 30 years out of date of optimizing things. I haven't done it for a long time, but when I was doing it, I don't know if you've heard the technique called simulated annealing. Mm-hmm. And I don't know if you've tried that and whether that would help.
Yes, in fact, I did try simulated annealing. That was my original choice of optimizer. The reason that I don't think it works so well in this case is because of that feature of the simplex method, which I mentioned. It tends to straddle the global minimum that you're trying to identify. And for the second stage of Bayesian optimization, right, having a straddle is a really useful feature. So I did try simulated annealing, but I found that the simplex method worked better.
I mean, that's assuming a simplex method doesn't get stuck at a straddles a local minima, yep. Whereas annealing jumps you straight, somewhere else completely to find the global.
Yes, it would do if you had an infinite number of simulator runs. Yeah. I think it's all about bang for buck here.
Yeah.
And my experience is that if you start off with quite a wide simplex for the downhill simplex method, so sometimes you have to intervene. In R, for example, it's not easy to set up the initial simplex. You can do it with the scale parameters in the control list, actually. So if you set up quite a big simplex to start with that covers quite a large part of your parameter space, then the downhill simplex method works quite well. Yeah, but if it makes its own choice about the size of the simplex and it starts off with a really small one, then it has to work really hard to make it bigger.
Okay, thank you.
Thank you. I've got a question from the online audience now. Jacqueline Asher has asked, she says, as I understood the example, calibration was to a single observed run, and in the real system we would have many runs with no flooding and occasional rare flooding events. How does this affect the fitting?
Yes, that's a really good question. So, in fact, one of the examples we're looking at the moment is more along the lines that she suggests, which is that, so we have a massive laser. There's a facility called the NIF. Can't even remember what NIF stands for, but it's at Lawrence Livermore. And it's the biggest laser in the world. And basically, you put a tiny sample into this massive laser, and you blast it with the laser, and then you see what happens. And we've done 2 runs, right, or 2 shots, if you like, with this laser. So we have a situation where we have 2 outputs. We have shot 1 and shot 2. And we want to match them both simultaneously because, as I described briefly, there are 2 parameters which are dependent upon which shot you're doing. So like there's... So you have to have 2 parameters for shot 1 and 2 parameters for shot 2. And then there are 2 more parameters, which are properties of the underlying physics, right? And the objective, of course, is to get to those ones. They're the ones that are really important. So in fact, we here have a 6-parameter problem. We have like P1, P2, right? Q1, Q2, R, and S. And it's R and S that we care about. So there, we are building a log likelihood function which actually merges those 2 runs together. So each run has got a 4-parameter log likelihood, but the 2 runs together have a 6-parameter log likelihood. And obviously that is extendable if you have more than 2 runs. So if you were the EA, I mean, typically the EA will tend to put a couple of big flood events through a simulator. You don't need to do too many different flood events because although flood events, big rainfall events on the catchment can manifest in different ways, there's quite a lot of filtering that happens in the catchment itself. So basically, by the time the water arrives at Hereford, the fact that you used a big forcing 1 versus big forcing 2 doesn't make a huge amount of difference. But if it did make a big difference, then yes, you would just create a combo likelihood by taking the sum of the 2 log likelihoods.
Any other questions from our audience? We have another online question here from David Smallbone. It says, please could you give some examples of where you have deployed these techniques alongside water modelling? It looks great and relevant in many real-world applications.
Well, to be honest, this is a response to work in progress. So I haven't actually used this in anger in anything but physics applications. But it was the case that in actually 3 different experiments that I'm currently involved in, the tuning is to a structured sequence of outputs. In one case, it's a time series of outputs. That's the NIF experiment with the laser. But in 2 others, the structure is more about where you are in a table. So that's a much more complicated situation. Just to reflect on my experiences in those situations, the thing that I found right away is a resistance to thinning, right? This is what happens because obviously it's really expensive to do these experiments and to collect a data point. Yeah, and I had the same experience with volcanologists. I mean, to go and excavate an ocean sediment, right, and to construct a measure of the thickness of an ash layer from an eruption that happened 80,000 years ago, that's a huge business. I mean, it costs millions of pounds and thousands of person-hours, to get the ship out there and to do all the stuff. And the idea that the statistician comes along and says, this is a fantastic observation, but I can't see how to use it because I don't understand its error characteristics, is, that's a difficult sell to someone who's spent millions of pounds on doing these kinds of issues. So I think this is work in progress. It's something we're currently doing in physics. I think my key takeaway from experience with the volcanologists and the engineers is not to talk about thinning, but to talk about feature extraction. And if there's one takeaway for those of you who have to work in these kinds of areas, I think feature extraction is the way to go, definitely.
Thank you. Anyone in the audience? Gentleman there, yes, please. If you could just go to the microphone, please.
Thomas House, University of Manchester. So following on from that, do you think there's room for using different distances? So you're doing some kind of L2 if you're doing a sum of squared, but the thing does seem worrisome because you might expect they're not IID. So could you do like a Supremum distance or Kolmogorov or Wasserstein or some of these other things? Would that be a way of assuaging their concerns in a principled manner?
So the answer, I think, in some situations is definitely yes. So I'm actually giving another talk this afternoon at 2 p.m. where I'm talking about reconstructing the deposition map of a massive volcanic eruption. And there I've gone down an entirely different route using an L1 norm and a massively over-parameterized basis function expansion. It's a different kind of problem, though. I took a much more empirical approach with that problem. What we have here, I think, is my attempt to construct a statistical model, right, in which I can embed current practice. And from that point of view, it seems very natural to assume that there is a transformation under which everything is normal and additive. I mean, that's why you do it, basically. And the transformation in this case was like a log of something plus a little. So basically everything is operating on a log scale. But that's why I came at it with this particular likelihood function in mind, because it was possible for me to show, right, within my model, that the engineering choice, which is almost invariably to minimize the sum of squared deviations, right, was a special case of my model, which looked like it was not capturing our beliefs about the underlying simulator. So I think there's lots of things that you would do, right, if you were starting from scratch with a problem like this, and probably everything wouldn't be normal and additive. I think you'd be much more creative about how you did the modeling. And how you captured the non-stationarity and the discrepancy and so on. There's lots of things that you would do here. But in the point of view of thinking about how we make incremental improvements on current practice, one is led immediately, I think, to a normal framework with additive effects.
I have another question online. It says, you talked about applying this to spatial data, and this is from Siddharth Rawat, I should have mentioned. Can this be applied to spatiotemporal data, and what would you think would be the challenges?
So the answer is yes, and we're doing something a bit like this in a very big project called Global Mass. Not quite the same, but it is a spatial temporal project. The issue for us there is it comes back to this GPS problem that I mentioned before. So again, imagine that instead of a time series, we have a large spatial domain like North America, and we have thousands of GPS stations on North America. And what we want to do in this project is we want to understand how the land is moving through time. So that the land is like a big spatial domain, and it's deforming in time. And it's got two types of deformation. One type of deformation is a very long-scale deformation that comes from the previous ice age. So in the previous ice age, ice pressed down on North America, especially on the top half of North America, sort of tilted the mantle, if you like. And then when the ice disappeared, those effects gradually wear off. Yep. So that's like a rebound from the last ice age. And then on top of that, you have much more local scale deformations, which come from the hydrological cycle. So it's draining of aquifers, it's raining, it's lakes getting bigger, lakes getting smaller, irrigation happening in some parts of the country and not other parts, and so on. So these GPS stations are really informative about both of those processes, but on top of that, right, they have their own individual characteristics because they pick up very local scale variations in space and time that are nothing to do with either of those two big processes, the glacial process or the hydrological process. So again, we would really struggle in that situation to take thousands of GPS stations and imagine the error structure, right, that captured the local effects of all of those GPS stations. And so the solution again is to go back and say, hey, let's not call it thinning, right? Let's call it feature extraction. But the fact is that you need to get rid, basically, of lots of the GPS stations in order that you get back to an error structure that you understand. Essentially, by thinning the GPS stations, you're filtering out, right, the source of variation that you don't know how to model. Now, when you're dealing with a spatial problem, I think you have two options. And I think I would deal with spatial problems differently from temporal problems. With temporal problems, I definitely thin. And that's because it's sort of, you can see the whole sequence, and you can see, in collaboration with your other scientists, what features of that whole time series are important, and you can extract those features, through thinning. But with the spatial problem, it's much more difficult. And in fact, you have two options. If the correlation length of the local features that you don't want to put into your statistical model is, say, 100 kilometers, you can simply remove enough GPS stations from your data set that the interstation distance is about 100 kilometers. So you can go into a cluster of GPS stations and throw out all but one of them, for example. Yep. That's thinning, and that's okay. But the thing that seems to work better, I think, and we've found in the Global Mass project, is aggregating spatially. So instead of throwing out lots of GPS stations, you dump down a set of tiles, with edge length of roughly 100 kilometers. And then instead of just keeping one GPS station in each tile, what you do is you take the arithmetic mean of all the GPS stations in the tile and you associate it with the tile. So you go from many point observations to aerial observations of arithmetic means of GPS stations. And the reason for doing it that way is, first of all, you're not throwing away any GPS stations and everyone feels happier about that. But secondly, there's a sort of a central limit theorem that starts to kick in, because when you take the arithmetic mean of lots of GPS stations, you can expect that at some level, some aspect of your statistical model becomes a bit more normal. So it turns out that when working with aerial data, I tend to favor aggregating to spatial polygons, but when working with time series data, I tend to favor thinning the time series. Now that doesn't completely answer the question. Spatial temporal is very difficult, but you've got to get each time point about right first before you start hooking them all together. And modeling the time point is something that's much better done, I think, with complex data structures by thinning or aggregating than trying to put everything in.
Okay. We have time for one more question. Is anyone in the audience here like to? Gentleman there, please.
Ayub Saeed from Public Health England or UKSHA from October. I got a stupid question, but let me thank you. Very fascinating talk, which woke up me from the sleeping. Fantastic talk. My stupid first question is, if you're trying to basically get to close what you observe, what this hustle muscle, putting lots of parameter or complex model to get what you observe. I will take the observed value, and then if I'm interested in the future, I just move one step down without estimating any parameter, because parametering is some sort of penalization. You bring the penalty, you reduce degree of freedom. This is really a stupid question, but And there is also, you talk about infit, but there is also outfit. How does it, that one? And my third question is, have you tried to use some sort of transformation? Because for example, log transformation reduce some of those, variation or whatever, so fit get much better. Again, thank you very much. Interesting talk.
Thank you. Yes, those are all good questions. I'll pick up on the first one because I think it's really interesting. There is a movement in hydrology which says exactly as you describe, right? We should throw away these Byzantine models of the catchment, and we should simply model the dynamic process that we're interested in directly, with transfer functions and so on, with a much more interesting dynamical model. And that's really good for in situ management. So if you're standing in Hereford right now and you're seriously worried about the fact that the river is getting higher and higher, right? It's very cheap for you to take an existing dynamical model of the river height and plug the latest observations into it and keep pushing forward. Yep? And that will give you a very good in situ assessment of whether you need to evacuate the city centre, for example. That's been advocated by members of the Lancaster hydrology group for a long time. The thing is, though, that doesn't allow you to do the kind of intervention studies that I tend to do more of in practice. So, if you're talking about climate change, or if you're talking in this case about flood modeling, the question is, can we create a simulator which is a test bed for things that we might do to evaluate their cost effectiveness? And there you really want your simulator to be as physical as possible, because of course you're going to make an intervention which is also a physical perturbation of the existing system. So you want your simulator to be able to capture the intervention that you have in your mind, and therefore it's got to have a physical basis. So it's often the case that if you're only interested in quality of fit, and you're interested in quality of fit, especially outfit going forward, you can do really well with a dynamical simulator. But if you're interested in intervention studies to develop policy, then you need your simulator to be as physical as possible.
Okay. Thank you very much, Jonty. It's now time to have a refreshment break, but before we do that, I'd like to thank everyone for being here in Manchester, thank all the people attending online, but of course, most especially of all, to thank Jonty for a fascinating talk. Thank you, Jonty.
Thank you. Thank you.